Okay, so for 2.1 notes, let's go back over derivatives and tangent lines again. So we already know the slope of a tangent line is called the derivative. This is what this whole chapter is about. Just to kind of remind you, f prime of x, which is what the derivative is the limit as h approaches 0, f of x plus h minus f of x all over h. Alright, so then we could say a function is differentiable. That just means able to take the derivative if the derivative exists. Okay, that means that there is a slope. And all the different notations would be y prime. What I'm saying is this prime, f prime of x. Sometimes we have dy over dx. This is because Newton and Leibniz both did calculus at the same time. So there's different, notations. All right, the prime, and then the d for delta, for change, having to do with derivative. So let's just jump into an example, because this is really how most of you learn. So for part A, to find the derivative, and what I'm doing here is I'm going to, redo this function with the limit so that I can find the derivative or the slope at any given x value. So I'm going to rewrite the function, but I'm going to have x plus h in place of just the x. So that's f of x. Then minus, now I'm just going to write the function. The rest is algebra. Okay, so still limit as h approaches 0. If I multiply x plus h squared out, now I'm going to go through this, and if you don't understand, you're going to need to ask me questions. This is all algebra. I'm just distributing and doing all those good algebra steps, distributing the negative. Now, if you did this correctly, things should start to cancel. And they do. If I work from the back, the plus 1 is going to cancel with the minus 1. The minus 3x cancels with the positive 3x. And the minus x squared cancels with the positive x squared. And what you're left with, still writing limit as h approaches 0, by the way, because I haven't taken the limit yet, is I can factor out an h from everything that's left. So I factor out an h from each of the 3 left. And what I can do now is cancel out h over h. I've now removed the whole when finding that limit. I would have got 0 over 0. Now I'm going to actually be able to plug 0 in for h. So this becomes 2x plus 0 plus 3. So I'm going to write it as 2x plus 3. Later on, we're going to talk about a shortcut for that. For now, let's continue. So the slope. When we say the slope at x equals -1, I'm saying what's f prime at -1? Remember, this is f prime of x. Okay? So 2 times -1 plus 3, that ends up being 1. Moving on. Tangent line. Now remember, to do a line, you need to know 3 things. We already are given the x. We just found the slope. Now to find the y, this is where people get mixed up. Just go back to the original. The y value is going to go to the original. -1 squared plus 3 times -1 minus 1. So 1 minus 3 minus 1, that's -3. That's the y value. So that should be equals there. So that's -3. Now also remember that we have point slope formula. So our final answer is y minus -3, so plus 3. M is 1, and then x minus negative is 1, plus 1. Okay, and you can actually just leave your answer just like that. Okay, next page. So now we have another example. Alright, so we're going to try this again. F prime of x is equal to the limit as h approaches 0, x plus h squared plus 2x plus h plus 5. You rewrite the function with x plus h in there instead. Minus x squared plus 2x plus 5 all over h. And the rest is algebra. Alright, so multiply that thing out. We get x squared plus 2xh plus h squared plus 2x plus 2h plus 5 minus x squared minus 2x minus 5. And it's still all over h. Notice I'm writing it out every time. Work from the back. Minus 5 cancels with plus 5. Minus 2x cancels with plus 2x. Minus x squared cancels with positive x squared. Now you should be able to factor out an h. So notice how it's like the same thing keeps happening. 2x plus h plus 2. I factored out an h from each of those terms. So now I have h over h canceling. And you go again. You plug 0 in for h, so 2x plus 0, I don't need to write that, plus 2. There you go. Now to find the slope at these x values, okay, you're going to use your derivative, f prime of x, and you're going to go f prime of 1. That would be 2 times 1 plus 2. That'd be 4. F prime of 4. That would be 2 times 4, which is 8, plus 2, which is 10. And f prime of 0 would be 2 times 0, which is 0 plus 2. Now part C is asking kind of similar. I need to be able to see this up here. It's saying f, there's no prime there. So they're really asking you for the y value right here. So f of 1, again, you just go back up to the original. 1 squared plus 2 times 1 plus 5. That ends up giving you 8. Okay, that's your y value. Your x is 1, your y is 8, and when x is 1, your slope is 4. We already found it up there. So I'm just going to go y minus y equals m, which is 4, x minus 1, and there is your tangent line. Okay, let's talk about differentiability and continuity. We already know what continuity is. Differentiable on an interval means differentiable at every point. Okay, this means that it has a slope. So you might think everything has a slope, but it doesn't. In fact, if something's not continuous, then it's not differentiable. So this means poles, vertical asymptotes, those things have no slope. Okay, also, this says just because a function's continuous doesn't mean it's differentiable. So we have something called a cusp. Sometimes cusps look like this. Sometimes they look like this. Okay, either way, it is a sharp turn. It's where the slope doesn't change gradually, it changes drastically. Okay, these things are continuous, but they're not differentiable. So this is a good example of something like that. Okay, vertical tangent line. This would be, one example would be where your function goes vertical just for a minute. Okay, also it could be a semicircle. Think about if I filled in the rest of this circle. The slope at these 2 points, that would be vertical. That slope would be undefined. So there is no slope right there. I don't mean 0, I mean it doesn't exist. So these are the examples of not differentiable. So just to recap, not differentiable if it's not continuous as a cusp or a vertical tangent, and then we have a theorem that states this. Okay, it's a one-way thing. Differentiable means continuous, not necessarily the other way around. Let's practice doing the derivatives on the graphs. First, determine the interval for which f of x is differentiable. Okay, also, this should be like this. Okay, remember, this is a cusp. Okay, I'm going to erase that because it's going to get in the way of my graphing here in a minute. So if I want to find where is this thing differentiable, it's differentiable everywhere except not at 4. Now, what I write here where this is differentiable is going to turn out to be the domain of my derivative. Let me go back. So this would be f. My derivative would say, okay, well, what's the slope of this line? It's -1. So what I'm going to do is graph the line y equals -1. So see, whatever the slope was becomes the y value. There's no derivative at a cusp, so I put a hole there. Then for this second half, the slope is 1. So I am going to, again, put a 0 and graph the line y equals 1. And that is how you graph derivatives. So we get a curve. It's a little bit more complicated. So what you want to look for is, where is the slope equal to 0? That's going to happen at maxes and mins. Okay, not cusp, but curve. So you may want to even write curvy maxes and mins. So see that? Max, min, max, min. The derivative, or the slope at those points, is 0. So I'm going to plot a point where the y value equals 0. Then I'm just going to take it a segment at a time. See how that slope is positive? Then my y value should be positive. It doesn't mean go up, because go up means left or right. You could change what go up means. But what this means is that it's above. Okay, look at this right here. This slope is negative, so I'm going to have y values that are negative, meaning I'm going to go down, then up again. Okay, this middle section, again, positive slope. So my y values are going to be positive, meaning they're going to be above. Negative slope, and you can kind of see the trend. You're just going through the points of that. All right, by the way, I skipped this, but where is this thing differentiable? Everywhere. Negative infinity to infinity. And notice that that ends up being the domain of the graph. So if you are just watching this and you wanted to try this one, go ahead and try this one on your own. Again, this one is differentiable everywhere. So first, identify your maxes and your mins. Then plot those as zeros. Then think, okay, slope, negative. Y value, negative. Slope positive, above. Slope negative, go below. Slope positive, go above. All right, here we have a graph with a vertical asymptote. I'm going to go ahead and plot it on here just to make it easier to see. So we're not differentiable everywhere. We have to skip over 0, because that's what the vertical asymptote is. And this should end up being the domain of my derivative graph. So right here, I do have a positive slope, but if you notice over here, the slope is close to 0. All right? And so my values. And as the x gets bigger, the slope gets bigger. So actually, the derivative here looks a lot like the original graph. Now over here, we have something very similar, except the slope is negative. Again, though, we have 0, and it should look something like this. So what you're saying is, what is the slope? And once you figure out what the slope is, then you're plotting the points with that same y value. Okay, semicircle's kind of weird. First of all, where's this thing differentiable? Well, it's not differentiable at -5 and 5, so it has to be between those two. So I'm going to write the interval -5 to 5, not brackets though. All right, so let's start with this point up here, because this up here, the slope is 0. So I'm going to plot a point at y equals 0. All right, and as I go kind of, all this slope is positive, so I should be above. But remember, I'm never going to reach -5, so I'm actually going to put a boundary, a vertical asymptote, and it's going to look something like that. Over here, I have a negative slope, so I've got to go below. But again, I can never reach 5, so something like that. Kind of looks like cotangent. That's interesting. Okay, so looking at the last one, differentiable everywhere. Well, let's say that this is going to go on and on, by the way, so we won't worry about that. But right there, we have a cusp. So I've got to skip over 0. We have no derivative at a cusp. There is no rate of change, no slope at a cusp. Okay, right here again, I have a line that has a derivative of -1, so I can actually just plot y equals -1. Put a hole for the cusp. All right, now we have some maxes, we have some mins, and if you see how this has a positive slope, I gotta go above. Now how far above, I don't know, but I know there should be a hole again because of the cusp. A negative slope, we should go below. a positive slope, we should go above, and that would continue on that way. Alright, if you're still needing help with the graphs, then what I want you to do is I want you to go to the website and go to those graph practicing websites.